Okay. So now when we combine power series, now if we want to consider the possibility of putting several power series together, we have a theorem that considers that. Power series are really just functions. So if we have a function that is represented by a power series, we can modify that power series in particular ways to come up with new functions. Let me show you what I mean. Suppose that the power series, sum of ck x to the k and sum of dk x to the k, where ck and dk are both constant terms that depend on k. Suppose that each one of those converges to f of x and g of x respectively on some same interval I. So maybe it's -1 to +1. They both converge on that interval. We have three rules about what we can do to modify these. First of all, if we were to take the sum or difference of these two power series, then it will converge to f of x plus or minus g of x on that interval. If we multiply by a power, suppose that, so if we were to multiply by, like, for example, x to the m, if we suppose that the m is an integer such that k plus m is greater than or equal to 0, then what we can essentially say is that when we multiply by x to the m times this power series, all we're really doing is throwing x to the m inside the power series. And it will converge to x to the m times f of x for all x not equals to 0 in I. When x is equal to 0, the series will converge to the limit as x approaches 0 of x to the m f of x. And finally, if we have a composition of functions, suppose that h of x is equal to bx to the m, where m is a positive integer and b is a non-zero real number, the power series ck times h of x to the k converges to the composition function f of h of x for all x such that h of x is an I. This is a super complicated theorem, but it's really actually super easy. It looks complicated, but it's not that bad. So let's do some examples. Suppose that we are just given the fact that 1 over 1 minus x is equal to the sum from k equals 0 to infinity of x to the k. In fact, we showed this earlier, right? We know this fact. We are now going to find the power series and the interval of convergence for the following functions. So x to the fifth over 1 minus x really is just x to the fifth times 1 over 1 minus x. And 1 over 1 minus x is just equal to this sum. And we know if we multiply by x to the fifth outside of the sum, we can just write it like this. X to the k times x to the fifth. We just put it on the inside of the sum, and we can add those together if we want to. Okay, and this thing is our new power series. All right, and further, we can say that this is still a geometric series, just like it was in the beginning, where the r is equal to x. So in order to converge, we still have that the absolute value of x is less than 1. And the interval of convergence did not change. In fact, in this theorem here, the idea is that your interval of convergence from the beginning will not change whenever you multiply by a power. Okay, so the interval of convergence is still going to be -1 to +1, and your radius of convergence is still just 1. All right, let's do another one. Once again, we are given this fact. And on an exam, you would most likely be given a fact like that, so that way you didn't have to worry about memorizing all the different power series representations. Okay. If we have 1 over 1 minus 2x, we can rewrite this. So actually, rather than trying to rewrite it, let's just notice this. Every time we have an x in this, we are just going to replace that with 2x. Okay, that's essentially what we're doing with the composition of functions. So this is f of 2x. This thing up top is really just f of x. So what we're doing is we're just going to replace it. So we know that this is equal to the sum from k equals 0 to infinity. Instead of x to the k, let's just write 2x to the k. This is our new power series. We're done. We're done. There's nothing more to do. This is the new power series. Okay, wasn't that easy? All we had to do was notice that the difference from the original function to our new function was that we replaced x with 2x. Okay, the only other thing that we would be asked to consider here is what the new interval of convergence should be. So, the idea is that if we go back to our theorem, it now says that h of x is in I. This will converge for all x such that h of x is in I. H of x in this case is 2x. So this will converge. This series will converge for all x satisfying absolute value of 2x less than 1. Right? Because the original series converged for absolute value of x less than 1, so we just replace x with h of x with 2x. And in this case, this means that negative 1 is less than 2x, which is less than 1. If we divide everything by 2, 1/2 is less than x, which is less than 1/2. And so our interval of convergence is negative 1/2 to positive 1/2, and the radius of convergence is 1/2. All right, let's do another one. Once again, same general idea. We are going to start with this thing, f of x is equal to that guy, 1 over 1 minus x, and we are given 1 over 1 plus x squared. So in this case, the idea is that we replaced x with negative x squared, right? And the composition rule says that our h of x has to be b times x to the m. So it's got to be some number times x to some power. And in this case, that's exactly what we have. We have b times x to the m. All right, so we can indeed do this thing where we write that this is the sum from k equals 0 to infinity of negative x squared to the k. All I did was replace this x with negative x squared. We can rewrite this as sum from k equals 0 to infinity of negative 1 to the k times x squared to the k. But of course that is just equal to negative 1 to the k times x to the 2k, if we wanted to write it like that. All right, and once again, this will converge for all values of x satisfying. So let me write, this is our new power series. Actually, let me not write it over there. This is the new power series. And so this will converge for all x satisfying absolute value of negative x squared less than 1. All I did was replace this x with negative x squared. So, absolute value of negative x squared, well, that is really just x squared. Absolute value of x squared less than 1. But the absolute value of x squared is just x squared because it's always non-negative, so we can write that this is just x squared less than 1. And if we take the square root of both sides, then we will get less than 1. And so let's be careful here. What is the square root of x squared? Hopefully you guys remember this. If you thought x, you are wrong. It is not x. It is the absolute value of x. Remember, square root of x squared is absolute value of x. And the square root of 1 is just 1. And so this gives us that negative 1 is less than x, which is less than 1. So a radius of convergence did not change. It is still 1, and the interval of convergence is negative 1 to positive 1, including neither endpoint. All right. We can also differentiate and integrate power series. So Theorem 11.5 allows us to do that. So rather than actually reading through this theorem with you guys, let me just read this note here on the bottom. The idea is that if you start off with f of x equals some series, equals some power series, you can take the derivative of both sides, or you could integrate both sides, and you'll come up with a new power series. The thing is, you should, the main interval of convergence will be the same, but the endpoints might change. So that's the only thing that you should consider checking. All right, so let's start off with this example. It's the same one we've got. F of x is equal to 1 over 1 minus x, and that is the sum from k equals 0 to infinity of x to the k. And we are going to differentiate both sides to find the power series for f prime of x. So we have, let me just write off the definition again. This isn't really a definition, it's just a fact. Let me write it like this. 1 over 1 minus x is equal to this thing. So this implies that we can take the derivative of both sides. So let me take the derivative of this guy like that. All right, so first of all, the derivative of the left-hand side, we can use the quotient rule here. If we do so, this will be low d high, so 0, minus high d low, So the derivative of the bottom is just -1 divided by the bottom squared. So 1 minus x squared. And the derivative of this sum might seem a little bit weird, but the idea is that in general, if you have a sum of terms, you can just take the derivative of each individual of each individual term. So we can write it like this. The sum from k equals 0 to infinity of d by dx of x to the k. All right, and if we were to do this, then we have the sum from k equals 0 to infinity. And what is the derivative of x to the k? Well, k is just a number, right? And so the derivative of this will just be k times x to the k minus 1. All right, so the thing here that you might notice is that we have a new power series that we can work with. We know that 1 over 1 minus x quantity squared is now equal to this power series over here on the right. But we can actually simplify this power series a little bit with some clever observations. The first clever observation is to notice that since this sum starts at k equals 0, the first term of this sum would actually be just 0 times x to the -1. So, to remedy that, we can just notice that this is the same thing as the sum starting at k equals 1, because the first term of that original sum was 0. Okay, the next thing that we can do is we can re-index this sum to make it look a little bit nicer. And the idea with re-indexing is if I want to instead start at k equals 0, since I reduced my index by 1, I am going to increase every k inside my sum by 1. So I am going to replace this k with k plus 1, and I am going to replace this k with k plus 1, so we get k plus 1 minus 1, which is just x to the k. And this is what we call re-indexing. This isn't terribly important. If you don't understand what I'm doing here, don't worry about it. This is just a clever observation that will help us later on. And so, what we have is that 1 over 1 minus x quantity squared is equal to this infinite sum. Okay, let me make this look a little bit nicer. Great. So, yeah, we can now write this function over here on the left, 1 over 1 minus x quantity squared, as that infinite sum. All right, so let me write this note. When differentiating or integrating, the interval of convergence will stay the same, except the endpoints might change. Okay, so what we can do now is we would check whether x equals 1 and x equals -1 converge or diverge to determine whether to determine what the new interval of convergence was. So for this example, the original interval of convergence before we differentiated was -1 to 1. And so now we have to check whether x equals 1 and x equals -1 will converge or diverge. So now check whether x equals 1 and x equals -1 converge or diverge. And I won't go through the details here, but it's actually not too difficult to determine that both of those will diverge. These both diverge. So the interval of convergence will be -1 to 1, and the radius of convergence will stay as 1. All right, let's do a similar example where we can integrate both sides of this power series. All right, so if we start with 1 over 1 minus x equals this infinite sum, we can integrate both sides. All right, so the integral of the left-hand side, we can use a u substitution to help us see what happens here. So if we were to use, let me change to a different color, we could say u equals 1 minus x, and then du would be negative dx. And so when we do the u substitution, we would get the integral of 1 over u times negative dx. So I'll just put the negative up here and throw the, times negative du. And throw that du right there. I'm going to keep the right-hand side the same for a second. All right, so the integral of the left-hand side is just the negative natural log of u. So negative natural log of the absolute value of u. I'll go ahead and say plus c. On the right-hand side, what we can do is we can switch the integral and the sum. Remember that the sum of integrals is the same as the integral of the sums. So if you have the integral of a bunch of terms, you can just take the integral of each piece individually. So this can be rewritten as the sum from k equals 0 to infinity of the integral of x to the k dx. Over here on the left-hand side, the negative natural log of u we can rewrite as 1 minus x. And over here, we have the sum from k equals 0 to infinity. The integral of x to the k is just going to be x to the k plus 1 divided by k plus 1. And we can go ahead and say plus c. Technically, this whole thing is inside of a parenthesis right here. So let me call this first C over here C1. Let me call this one C2. All right, and the details here are that if we consider what happens, let me do this. We can rewrite this now as the negative natural log of the absolute value of 1 minus x plus c1 equals the sum from k equals 0 to infinity, x to the k plus 1 over k plus 1. What we can do is we can actually consider this infinite sum from k equals 0 to infinity of c2. All right, well, in order for this thing to converge, this c2 must be equal to 0. So this thing just goes away. So this equals 0. Okay. Or actually, let me back up a little bit. I think that's not quite a valid explanation. Let me instead say this. We can rewrite this sum k equals 0 to infinity of c2. What if we add this constant over to the left-hand side? So, sorry, this should be a c1 right there. We're going to add this to the left-hand side. And so we are going to get the negative natural log of absolute value 1 minus x plus c1 minus that sum of c2. So I'm just going to call that whole thing a big C. Right? This is equal to the sum from k equals 0 to infinity of x to the k plus 1 all over k plus 1. And in order to determine what that big C should be, what we can do is we can set x equals to 0 and figure out what happens. So set x equals 0. And the reason that we can set it equal to 0 is because x is within this original interval of convergence, so we know that it will remain in the interval of convergence after an integration. So by setting x equals to 0, we can solve for the constant. We would get natural log of 1 plus c equals the sum of 0 over k plus 1. Natural log of 1 is just 0, and so we get 0 plus c equals 0, which implies that c must be equal to 0. So all of this was just to show that c was equal to 0. All right, and so what we essentially have here is that the negative natural log of 1 minus x is equal to the sum from k equals 0 to infinity of x to the k plus 1 over k plus 1. We could also rewrite this, make it look slightly nicer, that the natural log of the absolute value of 1 minus x is equal to the negative sum from k equals 0 to infinity of x to the k plus 1 over k plus 1. So whenever you look this up in tables or online or anything like that, this is essentially, or this is generally what you will see. Okay. And I will just go ahead and tell you that the interval of convergence here is equal to negative 1 to 1, including negative 1 but not including 1, and the radius of convergence is still just 1. I will encourage you to check this interval of convergence on your own. So figure out when or whether -1 and +1 converge or diverge. All right, let's continue. Now we are going to find the power series representation centered at a equals 0 for the series inverse tangent of x. So this looks really cumbersome, all right? And the thing that's difficult here is that we don't really know where to start. But the idea is that we just need to differentiate it or integrate it so that it is in a form that we are already familiar with. So we need to differentiate or integrate in inverse tangent of x so that it is in a form similar to a power series that we are already familiar with. All right, and the idea is that if we take the derivative of inverse tangent of x, this will be 1 over 1 plus x squared. And this is a form that we are somewhat familiar with already because we discussed this several examples ago with this guy. We know that 1 over 1 plus x squared is equal to this power series, -1 to the k times x to the 2k. So we will use that fact. So if the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared, we could write that the inverse tangent of x is equal to the integral of 1 over 1 plus x squared dx. That's just by integrating both sides. All right, and 1 over 1 plus x squared is a power series that we are familiar with. It is the sum from k equals 0 to infinity of -x squared to the k dx. And we already rewrote this, so let's do it again. This is the sum from k equals 0 to infinity of -1 to the k over x to the 2, or times x to the 2k dx. We can interchange the sum and the integral. So we get -1 to the k times x to the 2k dx. And one other thing that we can do is we can actually move the integral, or move the -1 to the k outside of the integral like this. The reason we can do that is because it does not have an x, and so it is treated as a constant with respect to the integral. And the integral of x to the 2k is x to the 2k to 1 more power divided by 2k plus 1. And we can go ahead and say plus c. If we continue on the next slide, if we plug in x equals 0 to solve for c, so let me write what we had. We had that the inverse tangent of x is equal to the sum from k equals 0 to infinity of negative 1 to the k of x to the 2k plus 1 over 2k plus 1 plus c. If we plug in zeros for x, then we will get the inverse tangent of 0, which is 0. We would get the sum of zeros, which is 0, plus c, and this implies that c is equal to 0. And in fact, this is super common whenever we do integration like this. So therefore, the conclusion, let me write it in a different color, is that the inverse tangent of x can be written as this power series. The sum from k equals 0 to infinity of negative 1 to the k of x to the 2k plus 1 all over 2k plus 1. And let's just stop to appreciate what's happening here. What we're essentially saying is that this function, inverse tangent of x, can be written as this weird infinite sum of x to the 2k plus 1 all over 2k plus 1 times negative 1 to the k. Like, who would have expected that? Like, that just seems kind of remarkable that we could even express a function like this in any way other than itself. We're expressing it as an infinite sum of polynomial powers of x. I think that's kind of remarkable, personally. All right, so the original interval of convergence, let me go back to green. The original interval of convergence was negative 1 to 1. That was for 1 over x squared. Or sorry, 1 over 1 plus x squared. And so if we check both endpoints, they actually will both converge. So we check both x equals 1 and x equals negative 1 to see if those converge or diverge. And in this case, let me I'll do one of these. Let's test x equals 1. So in this case, we'll have the sum from k equals 0 to infinity of negative 1 to the k times 1 to the 2x plus 1, which is just 1, all over 2k plus 1. And this is our series. We have to test whether this converges or diverges. So we use the alternating series test. All right, so the first thing we have to define is bk. We're going to define bk to be 1 over 2k plus 1. All right, and so let's just go ahead and take a derivative. All right, so we will get 0 minus It's low d high less high d low, so 0 minus 2 all over 2x plus 1 quantity squared. This is equal to negative 2 over a positive number. This is less than 0 for all x, so it is decreasing. Okay, and also the limit as k approaches infinity of bk is equal to 0, and so we have satisfied both conditions. So it converges at x equals 1. So the series converges at x equals 1. And if we did this for x equals negative 1, it would also converge. Also converges at, geez, why is it doing that? Also converges at x equals negative 1 by similar logic. And so the conclusion here is that the interval of convergence will be negative 1 to 1, including both endpoints, and the radius of convergence will be 1. Whew, all right, that's a lot. So let's go back and kind of just review what happened on this problem. We were originally asked to determine the power series representation for inverse tangent of x. We observed that if we took its derivative, we would get 1 over 1 plus x squared. And that is a power series representation that we are familiar with. We can write that in the power series representation. We can then integrate both sides. We get this guy. We solve for c. C in this case was 0. I think it is 0 in almost every case that you're going to end up doing. And then, whenever we, let's see, what was I going to say? Whenever we finally get to saying that c is equal to 0, we can represent inverse tangent of x as this power series, and then we have to test both endpoints from the original power series to see if those converge after we have integrated. Okay. For this final example, I actually want to leave this problem as an exercise to all of you guys. And in fact, I am going to award you extra credit for the quiz that is due on April 13th if you do this problem. And I'm not going to write down on the slide that it is extra credit because I want to give extra credit to the people who have actually been listening to these online lectures. So I am just going to write here that this is left as an exercise. Left as an exercise. And once again, the prompt is just the same as the previous problem. Find the find the power series representation for this function centered at a equals 0. And I'll go ahead and give you the answer here. The answer to this question is 2 times the sum from k equals 0 to infinity of x to the 2k plus 1 divided by 2k plus 1. And the interval of convergence for this thing is going to be negative 1 to 1. And the radius of convergence is also 1. And so if you just write down this problem on the quiz that is due on April 13th, then I will give you 2 points of extra credit. So all you have to do is just write it down. if you write down the problem and solve it, you can get up to 5 points of extra credit on the quiz that is due on April 13th. And yeah, once again, I'm not going to write down on here that it is extra credit because I want to advantage the people that have actually been listening to these lectures. All right, so yeah, make sure to just fill out all those details. If you have any questions about this problem, you're more than welcome to ask me about it, and I'll give you some hints. But yeah, that's all I've got for you guys for now. And until the next lecture, I will see you later.